My name is Kevin Goldstein, and we're here to talk about object pools, specifically object pools with the goal of performance tuning in a low latency application. Now, before we dive into what they are, let's quickly touch on what we're trying to solve, and that's a bad runtime profile. This is a picture that I think most of you have seen and are trying to fix. The application shown here will suffer from really long pauses and last random amounts of time. It will also be really hard to diagnose what the problems are, because sometimes methods will take 5 millis to complete and other times take 5 micros to complete. What makes an application like this so hard to deal with is that you have no control over when things start to misbehave. You basically run and pray. Now, what makes this a bad runtime profile? Well, look at the heap allocations here. Look at how it grows and drops between, 32 to 28, 32 megs, all the way up to 192 megs quite quickly. And you can see it in the graph here. And then it drops right back down. And you see this bandsaw picture here. The next hallmark of a bad runtime profile is the amount and frequency of garbage collection. Now, instead of this picture, what we want to see is a good runtime profile. And what does that look like? Well, it looks like this. And as you can see here, there's a very flat allocation rate on this heap. In this case, it's constant. And there is in fact a GC, but it also is only happening at the beginning of the application, not all the way throughout the application. Now, in case anybody's wondering, these graphs are not theoretical. These graphs are actually generated by code that we're going to be exploring during this presentation. While we'll definitely be exploring some higher level concepts about what an object pool is and how to use it, this is a down and dirty talk. We're going to be looking at code, we're going to be going into RDE, and we're going to be running stuff in a terminal. Okay, great. So what's our agenda? How are we going to do this? Well, first we're going to explore why use an object pool, which we already touched on a little bit, but we're going to talk about it a little bit more. Then we're going to discuss what they are. We're going to look at how to use them. I mean code-wise, right? And because we're going to be running applications, we need to see evidence of efficacy. How good is running an object pool versus running the exact same thing without an object pool? And then we're going to look at some of the issues with the solution that I'm providing here today and talk about some of the real-world requirements that any object pool you select might need. So why use an object pool? And the answer is quite simply stability and speed. Most people think of object pools for managing very slow things like database connections, file handlers, XML parsers, things of the sort. And the reality is, this is one of the best tools in your arsenal for building applications with a good runtime performance and stable runtime profiles, which is a very, very important aspect of any low latency application. So what is an object pool? And put quite simply, it's a way to manage allocation costs. What you don't want to do is allocate objects in memory when you need them. Instead, you want to manage that allocation. So for example, let's say you have a class A, and class A needs instances of some object. Instead of allocating individual instances of those objects, it's going to allocate an object pool. And that object pool is going to allocate multiple instances of that object. How many? Depends on its configuration and its capabilities, but multiple instances. So then, when class A requires an object, it simply takes one out of the object pool. Now, when it's finished, it returns it or puts it back into the object pool. And that's an important concept, because if you're only taking objects out of your pool and never putting them back in, that's called a memory leak, a quite large one in fact. So now that we've got the object pool instance defined, if class A needs an object from the pool, it just takes it. And if it needs another one, it takes that too. Now, let's say, for example, that another class in your application is doing something completely different and not related to class A at all, requires the same instance types. It can just take those out of the pool as well. It's important to realize here that you've now skipped over the allocation time of each of these objects. Instead, the maximum time that you're incurring is the time it takes for you to remove an object from a pool. Now, something that I want to bring up is that's present here but may not filter through to everybody are not static pieces of code. They're self-managed. In many instances, they get very, very complicated, and they have logic completely independent from your own. Right? An example of that kind of logic is that once an object pool sees that it's running a little bit low on its particular objects, it has the option of refilling itself, of generating additional objects in expectation of future use. Now, this is important because it's doing it out of band. It's not waiting for somebody to ask for it to allocate something that it doesn't have. Instead, it's looking at its internal state and saying, gee, I don't think I have enough of them. I'm going to pre-allocate some of these things in expectation that somebody else is going to request it. So how does it do this? Well, like I said, some of them can get pretty simple, but we're going to take the most basic version. And in the most basic version, this is just an array of objects. And when you create the array, you initialize it. And once it's finished initializing, you take things from the front and you add things from the back. And that's it. Now, what does it look like when you initialize it? Well, it literally is a for loop that looks like you're initializing an array. As you can see here, it's just running through this entire for loop, asking how many objects it's going to be creating. It makes sure that it creates that actual object. In the event that there's an error, it breaks. It creates that actual object and sticks it into the array. That's it. How do you take things from the front? Again, really easily. In this particular instance, the object pool, the array that I'm using is a deck, right? I can just take it from the head of the deck, and if I want to put it back, I just add it to the tail of the deck. It's actually quite simple. Now, some of you may have noticed this use pool Boolean flag. This is because we're going to be running tests on the exact same piece of code, and I didn't want to duplicate it, right? So I'm going to be setting a config flag at the beginning of each run, and then we're going to be able to see either it's taking something from a pool, or if that's set to false, it will be allocating something directly from its declared constructor. Great. So how do we know this is faster than actually allocating memory? And not only that, here's a better question. Is allocating memory so slow that I have to actually worry about it? Well, this test is sort of designed to answer both of those questions at the same time. So the question is, how do we test it? And the test is really simple. It's a for loop, and it takes stuff out and returns it to the object pool as fast as it possibly can. And it measures the time surrounding that operation, right? That's the measurement that it's going to do right here. And then there's some miscellaneous housekeeping stuff, such as keeping histograms of the latencies that we did it on a per second basis, writing that latency out to console, and making sure that it's running long enough for our purposes. Again, we're going to see the full version of this code inside the IDE, so don't worry about it. I'm just trying to get you situated so you know what to expect once we start looking at it. Another really good question that people ask when they start talking about object pools is, does it make a difference if you're allocating large objects or small objects? Well, we might as well test that as well. So what does a small object look like? It looks something about like this. It's got 1 string, 2 ints, and 2 doubles. And what does a large object look like? It's got 5 strings, 10 ints, 10 doubles, a byte buffer that we allocate up to a key. Right? So 1 kilobyte of memory is going to be allocated every time we allocate one of these buffers. Also, just FYI, when you see this in the IDE, it is going to be unrolled. So it's not going to be in array forms. It's going to be actual declared individually. All right, and at this point, I think it makes sense for us to switch over to our Eclipse. Let's have a look. As you can see, we have a basic interface for pool, which allows you to take and return an object. And we have a basic pool itself. Which, as we discussed, is implementing just an array. Now, inside here, we have a class builder for instantiating the object, as well as that Boolean flag of whether or not we want to use pool. Our default constructor, or our constructor here, initializes that Boolean flag. It also initializes that array to the starting position that starting size that we specify in the config file, and of course we keep track of that builder. We have an externalized initialize pool function that all it's doing is making sure something funky is not happening there, and then we initialize the pool if that particular field is enabled. Once we're ready, we go ahead and we add all the objects to the pool, and as you can see here, the object addition to the pool is quite simple. We're simply going to be using the default declared constructor and adding it in a for loop. The take object is pretty much exactly like we had in the presentation. It checks to make sure that you're using the pool. If you are, it removes it from the list, and if not, it uses the default constructor. and the return object basically puts it at the end of the list, and if it is not using pool, it just lets it go to the void, which means that the Java garbage collection is going to pick it up. So great. What are the objects that we're going to be using? We have the small object, again, same picture as what we discussed, 1 ticker, 2 ints, and 2 doubles. And we have a large object, which has 5 tickers, 5 ints, and 5 doubles, along with that declared byte buffer. As promised, they've been unrolled. Pretty much that's it, aside from the main application, where we're keeping that basic pool here. And a little bit of statistical and tracking information, such as the histograms file name that it's going to be written to. We build that out here, and then we start the test after it's been initialized. And the initialization is just that, setting up that histogram and that file, as well as initializing the pool with any of the settings that we've declared inside our properties. The start or the running of the object itself is quite simple. You open that CSV file, and here's that for loop where we're doing the measurement. We're taking nanotime, right? So this is the most granular level of time that Java can provide us. And what we're measuring is that take object and that return object. So what will happen here is this is going to remove something from the pool, add something to the pool, and then add it immediately right back to the pool, and we're measuring that time as granularly as we can. Outside of that measurement, we're doing some stuff. We are recording some values into the histogram, and we're also checking these stats to make sure we want to print that out to the log, to the terminal, which you can see here. Again, nano time, so this gives us whether or not we've changed time within a second, and then we're able to write things out to the terminal. And the rest of these the rest of these methods are simply for outputting information into the terminal and or file in a meaningful way. We want to see the percentiles and things of the sort. At this point, we're going to move into testing the small objects first. And if we move over here, we're going to see that we have configured the small objects, and we are not going to be using a pool. So let's just rebuild this sucker to make sure everything's running the way that it should, and make sure that the setting is correct. We are correct here. We're using a false, we're not using the pool to start out with. So we're going to, of course, when you want to look at the script that we're going to be running with, so that's run fr, and that's because we want to see how this is run. So as you can imagine, we're going to be enabling flight recording for 2 minutes, even though we're going to be running it for 1 minute. And that's going to allow us to look at our heap and GCs. We're also using the G1 GC collector, and we are going to be doing providing an XMX of 1 gig and an XMS of 512 megs. So great, let's run the first one, and we're going to call it no pool small. I will be varying the speed of this terminal output simply so we don't have to wait around for the whole minute to get these results. Some of the things that I'd like to pull your attention to immediately are it looks like we're allocating anywhere between 9.9 million and 10.1 million objects per second. We have a 50th percentile of 61 nanoseconds, 90th percentile of 63 nanoseconds, 99th of 69, and we really fall off the edge of the cliff here at 99.99th percentile, where we're looking at 18 microseconds. So let's let this finish up. Great. And in this instance, you can see we allocated just under 600 million messages, or actually, I'm sorry, 600 million objects in just under 1 minute. And we can see the outputted statistics of no pool small. We're going to open that guy up. Let's make this a little bit bigger so we can all read it. Great. And then let's do some averages here. So we're going to do 50th, 90th, 99th, and 99.9th. Average of E. And of course, because this is Java, the first two entries we are just going to throw away. And here you can see we've got some pretty good numbers of 60 nanoseconds on the 50th. Let's keep track of these in our presentation so that we can refer to them. So here we go. This is going to be 60, 63, 71, and 14917. Okay, so, and then let's open up our JFR of no pool JFR. Great. And if we come down here to memory, there's that bandsaw that we were initially talking about, right? That up and down between 64 megs all the way up to 320. Let's look at our garbage collection. And again, we see a boatload of garbage collections here. And as we zoom in, it's not looking that great. You know, you're going all the way up to close to a millisecond. And again, that bandsaw of memory allocations. And of course, these two things are tied to each other. As you execute garbage collections, the memory is going to drop. And as you run normally allocating objects, the memory is going to go through the roof. And you can see the garbage collections get better here toward the bottom, but at the end, we're still running 700, 900, and 800 microsecond garbage collection times. So that's not very good, especially not in an idealized world like this, where we are basically just allocating and freeing memory. Great, so let's now try doing the same thing with the pool enabled and see what kind of results we are going to be getting. So now we're just going to say pool small, bin run fr pool small. And you can see that I forgot to give it a starting pool size. Let's give it 100, which is okay because this is single threaded and just in a for loop. So we know pretty much we have a handle exactly on what this is doing, and it's okay to do 100. There you can see using pool true. And also, you know, the information is coming out here. A couple of stuff that I'd like to point out. Notice that we went from 9 and 10 million messages a second to 15 million allocations per second, not messages, I apologize again. 50th percentile has dropped down drastically between 29 to 30 nanoseconds. 90th is 31 to 30 nanoseconds. 99th is 37 to 36. And 99.99th is in the low 1 to 2 microseconds, with a lot of stuff dropping down here into the nanosecond level. Now, why is that? Again, is because we are measuring the time it takes to remove something from a deck instead of measuring the allocations of an object. And that, I can't stress how important that particular piece of information is. So we went from doing just under 600 million allocations per minute to 900 million allocations per minute. So let's have a look at what this looks like using our statistics as well. So we're going to open this guy up. Let's make him a little bit bigger so we can see. Okay, so we're going to have 50. And again, because this is Java, we're simply going to remove the top two entries, and we'll notice that these numbers are real small. So let's go ahead and record these as well. And we're going to say 29 nanoseconds, 31 nanoseconds, 36 nanoseconds, and 2, 3, 5, 4 nanoseconds. That is looking pretty good. Let's have a look at our JFRs. And if we look at our memory, this actually looks exactly like what we would have expected, right? Here we are, sorry. We have an incredibly flat, let's look at this from the garbage collection instead. We have an incredibly flat heap. In fact, no heap here. Again, this is an idealized run scenario, but you can see the stability that this approach brings you. We've got one giant garbage collection that took us 6.6 milliseconds here at the beginning of our application, but no more garbage collections here. As you can imagine, this is going to lend you quite a bit of stability within a more complicated and realistic scenario. So great, let's go look at, let's close this guy out. Let's go look at what this is going to look like when we run them with large objects. And how do we do that? Well, I don't really have an elegant way of doing it, so I'm just going to replace the code here of small object with large object. Replace all. There should be 4 replacements. And 1, 2, that looks correct. 3, yeah. And I know that there was 4 because it said it at Eclipse. So great, we then have to recompile. So npm clean install. Oh, I actually have to save it. Clean install. So that goes nice and running. Let's make sure that this is false as well, and then we're testing what we think we're testing. So we're going to say script run fr as no pool large. Notice the pool false, and look at what a difference we see. Right off the bat, we are down into the 4 million object allocation per second range. The 50th percentile has dropped down to 130 to 150 nanoseconds. Also notice the 50th percentile and the 90th percentile used to look like each other, and now they don't so much. I mean, it's not so much as double, but between 50th and the 99th, that certainly is double, and the 99.99th has truly fallen off the edge of the cliff, where we are consistently into the 20 microsecond area here. So we have definitely seen a much larger degradation because of a larger object usage, and that makes a lot of sense. So we have just over 270 million object allocations in 1 minute runtime. Let's have a look at our statistics, of course. So we're going to go to no pool large. Make this guy a little bit big. Oh, too big, so we can see. And of course, we're going to throw away the top 2 rows here. And there we go. That looks about like what we were seeing. Let's go ahead and record these values. So we see 142 nanoseconds on the 50th, 203.430 and 21117. So 2117. Okay, let's close that guy out, and let's have a look at our JFR. Great. And oh my God, this is in fact gotten worse. This is a nice solid purple band. Pretty much exactly what we expected. Just more the same that we saw in the small object pool, just a little bit more pronounced. And if we look at it from the point of view of garbage collection, we see the same thing, a very large garbage collection at the beginning and lots of little garbage collections. As you zoom in, the behavior is definitely something that is cause for concern here. So if we close this guy out and we do the if we run the exact same test using ObjectPools, notice the true, and what are we seeing? Wow, what a difference. It is back down to the 29 or 30 nanosecond time in the 50th, 30 to 32 nanosecond time in the 90th, 99th percentile is showing 36 to 45 nanosecond time, and the 99.99th percentile is that 1 to 2, maybe here on the higher level 3 microsecond times. Our count rate is back up to 15 million, high 14 millions, low 15 millions. And again, this is because we're now measuring the time that it takes something to take off the queue, not the time that it takes to allocate. I can't stress that point enough. Let's wait for this to finish so we can have a look at some of our statistics. There we go. And just under 900 million allocations in 1 minute. That looks actually really good. So this is also showing that by using object pools, you're not actually incurring any additional cost by changing the size of your objects, right? So if one day you add another 10 fields to one of your market data objects or another of your order objects, your application profile should not change. That's a very important point, right? That gives you stability during evolution of your development cycles. So great, let's look at pool large and make this bigger so everybody can see it. Great. Okay, great. And let's record these numbers as well. So we've got 29 nanoseconds in the 50th percentile, 30 nanoseconds in the 90th percentile, 37 nanoseconds in the 99th percentile, and 2,126 nanoseconds, or 2 microseconds in the 99.99th percentile. That is an impressive drop. Let's also check out our JFRs. I'm pretty sure we know what it's going to look like, but we need to just do it for completeness. I mean, we are here. So if we look at memory, yep, there's absolutely no memory allocated there. The same amount of memory the same picture that we saw with the small object pools, even though we are taking up a little bit more memory. If we look at it from the point of view of the garbage collection, the same thing here. One very large, long garbage collection that's happening at the beginning, and then a pretty stable heap and no garbage collection interference throughout the application profile while we were running them. Okay, so we're going to close this thing out. And at this point, let's flip on back to our presentation and go from back to here. Play from current slide. Okay, so what have we learned after having run this? So we're now in the evidence of efficacy phase of the presentation, right? And we know that, I'm just going to do a quick recap of the results. We know that even from the small object point of view, we are going to have almost a double increase in speed, right? 60 nanoseconds versus 29 nanoseconds, 63 nanoseconds versus 31 in the 90th percentile. And here's an important drop, 2 microseconds versus 14 microseconds in the 99.99th percentile. And this is important because, as most developers know, it's somewhat easier to get to the target numbers that you're hitting in the 90th percentile and lower. That last 10% is real hard. And object pools are one of the tools that allows you to have that stability on your runtime profile, which is something that people are always looking for. The results from a large object pool are also equally impressive, or more so. We have now picked up close to, 4 times the speed. 90th percentile is 203 nanoseconds versus 30. 99th is 430 nanoseconds versus 37, and 99.99th percentile is 21 microseconds versus 2 microseconds. So we're looking at a full order of magnitude there. This is definitely a lot of bang for your buck. So what's wrong with the implementation that I provided here? Obviously, this is the most basic of all versions of object pools, and I think most people are going to latch onto the fact that it's not thread safe. In fact, I'll argue that that's not an implementation problem. That depends on the use case. However, the single largest problem with this particular object pool is that each of the objects are not being zeroed out when they're put back in to the object pool. There's many different ways of doing this, but let me explain first what I mean by that. When you take something out of an object pool, you have to be sure that the fields of that method are pristine, that you can use them without any fear of having any data corruption from previous use. So let me give you an example. Let's say we have two tickers, right? Let's say you've got an object pool of orders, for example, and you've got two tickers, and somebody places an order for AAPL to buy 2,000 of them at price 300, and then they buy BP. Another order comes in, and they are going to buy it at 2,000 shares at 23.50. And both of these instantiations come out of an order object pool. So the first time that you get it, you're going to fill in your character list with AAPL, right? And the second one that you get it, because it's going to be the same object, is going to be added in BP. However, if you forgot to clean out these last two letters, right? The order that may be going out to the market is that BPPL, because you're not replacing a full string, you're writing a low latency system. You're going to replace as little as possible. You're going to replace the size of the ticker that you're dealing with, which means that the order going out to the market is BPPL. I don't even know if that's a real order. And when suddenly people start asking you to define where did this order come from, you're going to start going through your logs, and you're not even going to find BPPL coming into your system, yet somehow, in somewhere, it got introduced to it. So this cleansing of data is actually quite important. And it needs to be added in there. Obviously, this adds complexity to your implementation, and complexity is going to increase latency. And one of the things that many people end up considering is which fields are required to be zeroed out. Tickers are a great example of something that is absolutely required to be zeroed out. So you have to be cognizant of which fields are going to be zeroed out, and either you zero out everything, or your pool has to support key field zero outs. And that brings us to the next point of what do you look for when you're dealing with object pools, and what issues do you have with dealing with object pools? Let's talk about the issues first. When you move to working with object pools, you've now changed the memory model that you're working on from Java. Part of Java's allure is that developers don't have to worry about it. Yeah, you create memory, and then you when you're done with it, you throw the object away, and the JVM will take care of garbage collecting that object. We have now moved into a different paradigm where you are in fact doing memory conscious coding. And like I said before, if you forget to return something to the object pool, that's called a memory leak, and that's not something that you want to have. So this also adds complexity to your code. It is more difficult to manage an object pool because not everything is such an easy example where you're taking it single-threaded in a for loop from one object to the other. And most commonly, you're pulling something out of an object pool, you're populating it, you pass it to a handler, that handler passes it to another thread, that thread passes it to another handler. When you finally decide that you're done with it, whoever's done with it has to remember that they need to put it into, to return it to that pool. It's not always that easy to know when you're done with it as well. And it's probably object pools, while incredibly useful and provide you the stability and speed increases that you are looking for, are probably one of the easiest ways to introduce memory leaks into your system if you're not careful. So great, what kind of things are you looking for in an object pool? And that's not always so easy to solve. A lot of the object pool implementations out there are a little bit too large, or they're not difficult, they're not easy to use. Ease of use is something that's actually quite imperative, right? So Your pool has to support non-default constructors, for example, making sure that an object was validated while it was being put into the pool, making sure that object was zeroed out when taking out of the pool. Hopefully, it supports different policies. Do you zero out an object when you're taking it out of the pool, or do you zero out an object when you're returning it into the pool, right? You want it to be as efficient and fast as possible. Perhaps more overhead is agreeable when you're returning it to the pool because it's going to be out of band. There are many different configurations and many different policy decisions that you can make that have to be right for you, your application, and your environment. However, you also want it to be somewhat configurable. Does this mean that the object pool is going to grow as needed, or does it have a constant size? Is it thread safe? Is it using mutexes, or is it using spin locks? And how does it tell the difference when to use which and which one? Is there an in-band cleaner or cleanser, that zeroing out capability? Do you clean things when you're taking them out of the pool, or do you clean things when you're putting them back into the pool? When you're putting them back into the pool, does it put it on a temporary queue for cleaning and have a separate thread take care of that? And then make them available, or what? There's a lot of configuration that goes into object pools, as well as the object recapture capability. A lot of these pools try to provide the GC style approach, that once you're done with an object and everybody's lost references, it'll be automatically reclaimed by the pool. But again, complexity and time suddenly start creeping into that feature set very, very quickly. And lastly, and this is an important point, it needs to be queryable. Anytime that you're introducing these kinds of data structures into your environment, you need to be able to ask it questions. You need to know how many objects are allocated, how many objects have been removed in the last second, 10 seconds, 50 seconds, how many objects are left, the size of the pool, things of the sort. Once you suddenly have a pool and you start using it, and you then need to debug it without being able to query it, debug becomes quite difficult. For example, without being able to know how many objects are currently in the pool, it's hard to see if somebody's never returning them, for example. There's a lot that you can do from the debugging perspective and the runtime profiling perspective that makes queryable statistics from that object pool an absolute must. And I think that's it, guys. I hope you guys enjoyed this presentation on object pooling. Please feel free to contact me with any comments or questions, and happy coding.